To look at simple linear regression and multivariate regression, we'll look at a data set that stemmed from a paper published in the 2000s about colorectal cancer rates by country and the type of diets in aggregate that those countries consumed annually. This data set is made up of almost all continuous variables, with the exception of the country designation and then an olive oil consumption variable that is listed as low or high. Our outcome here is actually the overall colorectal cancer rate here at the end, which is an aggregate of the male and female cancer rates. Each of the variables looks at the amount of consumption per capita in each of the countries. So let's first start with looking at a distribution of our outcome, which is the CRC. And then let's look at meat consumption and fish consumption. So we can see here that we have 28 countries represented in this sample data set, with colorectal cancer rates going from 4.6 to 38.4. Meat consumption rates, also a wide range, and then fish is on the lower end. So you can see more consumption of meat per capita than fish per capita. Then let's take a look at the simple linear regression for colorectal cancer and meat. So we can here again put colorectal cancer as our Y and meat consumption as our X and press OK. We can see here the scatter plot shows us that a line fit would be appropriate, probably about through there. And we can ask jump to fit the line. And in this, we get the analysis of variance, which is our whole model test. Remember, we're asking the question, is meat predictive of colorectal cancer rates? Or is our best guess for colorectal cancer rate the mean value for CRC? The answer to that question here with a very small p-value is that yes, meat is helpful in predicting colorectal cancer rates. And we can tell from here that this is a positive relationship. So for every 1 unit increase in meat per capita consumption, the colorectal cancer rate goes up by 0.233. You can see here with our intercept that if a country consumes no meat products, they will still have an average rate of 8.3. So in this case, an intercept makes sense. We do know that people can develop colorectal cancer rate without consuming meat. So an intercept here makes sense. And our conclusion here would be that meat consumption is found to be associated with colorectal cancer rates by country, such that every 1 unit increase in meat per capita consumption results in a 0.23 increase in colorectal cancer rates, p-value less than 0.0001. You could also report the R-squared, that the meat accounts for 53.1% of the variability in colorectal cancer rates, which is actually quite good. This is a relatively strong predictor in terms of adjusted R-squares for a single predictor. So what about fish intake? Let's take a look at fish by itself. Fit Y by X. Again, colorectal cancer rate as our Y and fish intake as our X, and press OK. So we see here a little bit of the opposite effect. We're looking at maybe a line that's either going to be a little flat or perhaps have a little bit of a downward turn. Let's go ahead and ask jump to fit the line. And remember, our question here is does the per capita fish consumption predict CRC, or is the CRC mean estimate our best predictor? And in this case, our p-value is telling us no. Fish is not a useful predictor on its own of colorectal cancer rates. We have a large p-value here. Our R-squared is very low, so explaining less than 5% of the variance associated with CRC. And so we would have a quick sentence that Fish consumption, per capita consumption alone is not predictive of colorectal cancer rates, and give the p-value. Give the p-value here, and we would be done. But we know that people's diets consist of more than just one component, so it may be helpful to look at components together when predicting colorectal cancer. So now let's take a look at FIT model. Colorectal cancer rate is our outcome. Let's put meat and fish into the model together and press run. Now remember, the first thing that we need to look at is this analysis of variance test. Our null hypothesis here, again, is that the average colorectal cancer rate, shown here with this blue line, the average colorectal cancer rate is the best estimate of colorectal cancer rates. Our alternative hypothesis is that this model is a better predictor of colorectal cancer rates. We use this p-value here in the analysis of variance to answer that question. Again, the p-value is very small, and it is telling us that this model is useful, that we get a better prediction of colorectal cancer rates with these predictors. Now that we've answered that question, we can go ahead and look at the parameter estimates. Now, we're not surprised to see that meat is statistically significant. We saw that before, that there was a very high prediction using meat per capita consumption of colorectal cancer rates. And in fact, if you look at our parameter estimate here, a 0.24, it's very close to our predictor before, that the presence of fish in the model has not really changed the way that meat predicts colorectal cancer. But what we do see here is that fish is now a statistically significant predictor of colorectal cancer in the presence of meat consumption. And you may say to yourself, this seems really weird. We thought fish wasn't related. Well, it turns out the way that these models work is that when the highest predictor, meat, is used, it doesn't do a perfect job of predicting colorectal cancer rate. When meat is used, there's some error left in our model. Remember, it predicted 53% of the variability. So that means that there's 47% of the variability of CRC left over to predict, and it turns out what is left over, fish does a good job of eating up some of that error that's left over. So while fish alone did not do a good prediction of colorectal cancer, fish in the presence of meat, or when adjusting for the meat consumption, fish actually adds some useful information here. So in both cases now, we have significant variables. And so this is why modeling is very important. Simply doing unadjusted is what they're called, bivariate analyses can be very useful in a number of situations. But always make sure to consider the possibility that there may be more than one relationship that you need to consider at a time. So for this analysis, what you would do is report the average colorectal cancer rate, the number of countries that you have. You would report the mean meat and fish consumption with a standard deviation for each of those variables. You would say that the prediction of colorectal cancer rate is improved by the use of meat and fish with this p-value, and that meat and fish together, using the adjusted R-squared, account for 60% of the variability in colorectal cancer. For every 1 unit increase in meat per capita consumption, colorectal cancer rates increase by 0.23. For fish, it's by 0.15. If you would like to look at the way that this changes, you can go to factor profiling and look at the profiler. And this is a figure, again, that is useful only for JUMP, but it can be helpful to you in terms of looking at how the relationships work. So in JUMP, this prediction profiler allows you to move along the meat consumption line, and you can get a predicted colorectal cancer rate with a 95% confidence interval for each of these levels of meat. So let's say I wanted to look at a 60 per capita consumption of meat and then 40 of fish. you can then see here's my predicted colorectal cancer rate. If I hold meat there at 60, I can see what happens as I increase the fish consumption or lower the fish consumption. And then if you wanted to graph this data, you could actually output a table of values here that have taken a section of meats and fish values and giving you some outcomes of colorectal cancer. And then you could go into Graph Builder and we could take a look at putting CRC here and putting, say, meat on our X value, and it gives us a fit line. And then if we overlaid that as well with fish, or you could overlay it with fish here, and this will show you that for low levels of fish consumption, as meat increases, here is what our prediction would be, so forth and so on. Makes a nice graph for displaying colorectal cancer rates. So that in a nutshell is colorectal cancer rates using multiple linear regression.